Good day. In this video I would like to introduce some of the exercises from exercise set 1. These exercises relate to inner product spaces and norms. I'm going to start with exercise 1.4, which I have copied here. Let me read the exercise. It says, given a symmetric positive definite bilinear form A of xy, define this symbol, which I can call norm A of x, is defined as A of xx to the 1/2 power. Now remember, A refers to this bilinear form. A takes two arguments, which are two vectors, x and y, and I want to create a function of x only and the way I create a function of x only is I put x in for both arguments. So I could actually give an example of this. Now this is only one example. So for an example, we'll let this here, this parenthesis with two arguments, denote the usual inner product. And let's say the usual inner product on our n. This would be n-dimensional space. Now the usual inner product can be written like this, parenthesis x comma y. You may know this as x dot y. It's the same thing. I can define this as x1 y1 plus dot 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 plus xn yn. I'll just remind you that x indicates this vector with n components, and y indicates this vector with n components. All right. So in this case, the usual inner product is this sum here, which we can write this way: summation j equals 1 to n of xj yj. Now I emphasize that this is only one special case. This is not general. I want to prove a property for the general bilinear form. So you cannot use this formula in the proof of this exercise. I only want to give an example. Okay. Alright, so if this is my inner product, then I could define the norm of x as equal to the xx to the 1/2. All right. Now what is that? If I use this formula and I put x in place of y, this is substitution again. This will give me x1 times x1 is x1 squared. And I'll have n terms. The last term is xn squared. Okay. And then I take the square root of this. So I can write this, of course, as this way. Square root of sum j equals 1 to n xj squared. Okay. Now I hope you can recognize this as the usual Pythagorean or Euclidean norm. Now I do want to emphasize that this is just a special case. It's not general, but it shows you why I chose this definition for the norm. All right, this norm for the usual inner product agrees with the usual norm. Okay, now so that's explaining this topic here. Okay, let's go on and continue the problem. Suppose also that the absolute value of a of x comma y is less than or equal to norm a of x times norm a of y. Right? These bars indicate absolute value. Now remember, A is a symmetric bilinear form, so A of x and y is a number. It's a real number. I can take the absolute value of a number. Now we do know that A is positive definite, but that only means that A of xx is non-negative. A of xy can be negative, so I need to take the absolute value here. So suppose that this relationship holds. I want to show that in fact this norm A satisfies the triangle inequality. Now, you may be familiar with triangle inequality. Just to review the notion of triangle inequality, the triangle inequality says as I said, it's the norm of x plus the norm of y is greater than or equal to the norm of x plus y. And this has a geometrical interpretation. Okay. So if I take this norm as the usual geometric meaning, now the usual geometric meaning of norm is the length. Okay, then I have a geometrical interpretation. Okay, my geometrical interpretation looks like this. Here's my vector x, okay, which I can represent as an arrow. And here's my vector y, which I can also represent as an arrow. And my vector x plus y is found by adding these two arrows head to tail. That's how vector addition is represented geometrically. All right, so my x plus y is here. Okay, so you can see that the length of the long side here is less than or equal to the length of x plus the length of y. In fact, we know that the straight line from one point to another is the shortest distance between those 2 points. So x followed by y also goes to those 2 points, but x plus y goes directly. So we do have the length of x plus y is less than or equal to the length of x plus the length of y. Okay. All right. The only way that you can have equality is if x and y are parallel. Okay. Okay. All right. So I want to show that in general, if I have an arbitrary bilinear form, now let me remind you that, so we want to prove this. So we want to prove a similar result for an arbitrary bilinear form. Okay, since we're doing arbitrary linear form, we need to use an algebraic proof. The proof has to be algebraic because we have defined the arbitrary bilinear form in algebraic terms. Okay, so you must use an algebraic proof using the properties of A. Okay, now what are the properties of A? The properties of A are as follows. A is positive definite. Okay, if A is positive definite, that means if A xx is greater than or equal to 0. Okay, and AXX equals 0 if and only if x is equal to 0. We know that A is symmetric. Okay, A of xy equals A of yx. And we also have A is bilinear. So we have A of C1 x1. Well, let's do x and x prime is how we've been doing it. C1 of x plus C2 x prime y equals C1 A of x y plus C2 A of x prime, sorry, there's no parenthesis there, C2 times A of x prime y. And we also have A of x, I can say d1 y plus d2 y prime is equal to d1 A of x y plus d2 A of x prime. Sorry, not x prime, xy prime. Okay. Okay. So let me emphasize that you need to use these properties and the definition of norm A, which is given here, the definition of norm A, to prove this statement. Okay. Now, if you need help, please contact me. I can give you some hints. You can send me your work as a screenshot, and I can help you along to prove this exercise. It's not a very complicated exercise, but it shows how to use these algebraic properties. All right, let's go on to the next problem. Excuse me. If I talk about the components of a vector in a vector space, components of vector in an n-dimensional vector space. Okay, so I'm going to let V be an n-dimensional vector space. Okay, and I'm also going to let B1 through Bn be a basis for V. Now what this means is that any vector in V which I could call x, for instance, any vector x which is in V can be written as x equals C1b1 plus C2b2 plus dot 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 plus CNbn. Okay? All right. Now these C's here, the C1, C2, and so on, these are the components. These are the components of X relative to basis B. Okay, so I'll call this basis B like this. Okay? Okay. So this exercise 1.5 has to do with finding the components of X relative to a basis B. All right, so let's take a look at the problem. Okay, 1.5. And where are we? Okay, so I'll get my screen clipping. Exercise 1.5. All right, so I'll clip this also, just so that we can see what's going on. Okay, and let me move it over here. Okay. Okay, let me make it a little bit smaller so we can see it. Okay, all right. So that gives us the equation. All right. Okay. All right. Now, the first question here is just a question of definition. Given a vector space with basis B1 through Bn, give necessary and sufficient conditions for the basis to be orthonormal. So you need to understand this notion of orthonormal. So if you do not know what orthonormal means, you can look this up in a resource on linear algebra. Please consult a textbook on linear algebra. Okay, you should review this concept Now, I gave a link to a textbook on linear algebra in the Canvas webpage, but you should have had a course in linear algebra. Okay. Okay. All right, so I'm not going to say more about that, but the idea of orthonormal is a generalization of the concept of perpendicular. Okay, realize that. Okay, and then for example, the standard basis is orthonormal. What is the standard basis? The standard basis is the consists of the vectors which are the rows of the identity matrix. Okay. For instance, in R3 we have the standard, if we have the identity matrix, okay, for example, in R3, I have the identity matrix as 1, 0, 0, 0, 1, 0, 0, 0, 1. So the standard basis is equal to E1, which is 1, 0, 0. And we often put a hat over it to indicate that it's a vector of unit length, E2, which is equal to 0, 1, 0, and E3, which is equal to 0, 0, 1. All right. All right. So these are just some illustrations. To ask this question, please just give me a definition of orthonormal. I'm given this basis, give me a definition of orthonormal. Okay. All right, so let's go on to the next question. Let me scroll down here. Where am I? Okay. We'll go to the next place here. All right, now, exercise 1.6 says, given a vector space with an orthonormal basis, B1 through Bn, give a formula for the components of a vector V in terms of inner products. Okay. Okay, let me again give an example to illustrate this. I'll give a very simple example. Okay, so let's do an example. Okay, I'm going to take my vector space as R3, and I'll take my vector V in R3 as 3, 6, minus 2. Okay, that's a vector in R3. Now you may be used to writing vectors as 3i plus 6j plus minus 2k. I am using this notation because it's more convenient. It's difficult to write vectors in the other notation if they have more than 3 components. Okay. So let me take as my basis the standard basis. Okay. And that's equal to E1, E2, E3, which I've just defined above. Okay. Now I want the components of V in terms of this basis. So I can write V as equal to, well, if you notice what E1 is 1, 0, 0. So in fact, this 3 in the first component, in the first place here, is 3 times E1. Okay. The 6 in the second place is 6 times E2. And this minus 2 in the third place is minus 2 times E3. Okay. All right. So these are the components of V. Okay. But I want to find these as I want to find a formula for these components in terms of inner products. Okay, so now if you notice that in the usual inner product, we write, the usual inner product is x1, y1 plus x2, y2 plus x3, y3. So note, for example, if I take the inner product of v with E1, what do I get? Well, that's going to be 3, 6, minus 2. Now we can write the inner product as a dot product with 1, 0, 0. Okay? And so that's equal to 3 times 1 plus 6 times 0 plus minus 2 times 0. And that turns out to be 3. Now what a coincidence. Here we have a 3 up here, and here we have a 3 down here. Now is that really a coincidence? So what we found is the component of V in the direction of E1 is V inner product with E1. So let me just write that down. So I want you to generalize this fact for an arbitrary basis B in an n-dimensional inner product space. Okay, so what you should end up with is a formula. So you should provide a formula as follows. All right, given some vector v is equal to a1 b1 plus a2 b2 plus an bn. Okay, where b1 through bn is an orthonormal basis. Okay, you want to find a formula, so provide a formula of the form aj, which is the jth component, is equal to something. And this something should involve inner products of V with basis vectors. Okay, so I want an expression here that involves V and the inner product of these vectors. Okay, and then I would also like you to prove your formula. Prove your formula. Don't just give a formula. Show me why it is true. Prove why your formula is true. So, for example, again, I'll go back to my original example. Okay, suppose I have V is equal to what were the examples here I used? 3 times E1. Now this is not dot product. This is just multiplication, right? Because 3 is a number and E1 is a vector. 3 times E1 plus what was it? 6 times plus 6 times E2 minus 2 times E3. Okay, so we can take the inner product if I take the inner product of V with E1, okay, that's going to give me this inner product, 3 times E1 plus 6 times E2 minus 2 times E3. That take the inner product of this with E1. Now I can use the bilinearity of this to get the inner product of 3E1 with E1 plus the inner product of 6E2 with E1 plus the inner product of minus 2E3 with E1. Now that's equal to 3 times the inner product of E1 plus 6 times the inner product of E2 with E1, okay, plus minus 2 times the inner product of E3 E1. Okay. All right. Now, what does orthonormality tell me? Okay, sorry, I lost this. Okay. Sorry. Orthonormality tells me the values of E1, etc. Okay. Because I know this is an orthonormal basis, I can find the values of these. Again, I say orthonormality relates to perpendicularity, so you should be able to understand the values of these inner products. Okay, so some of these inner products will cancel. Okay, and my result will be that that VE1 is equal to 3. Okay. Now you see that this result has this form that I'm looking for. I'm looking for the component is equal to some expression involving inner products. So I should write it this way. Instead of writing it this way, I should write 3 equals VE1. Okay, so this is one specific example. I want you to generalize this. Okay, and prove the general formula. Okay, the proof of the general formula is very similar to this procedure that I've showed here. All right. So let's move on to the next one. I think I will stop with this video here and do another video for the next few problems. It's better not to have a video that's too long.